Okay, welcome to part 3. So what we have here, and I'm just going to use the book on this one. It's actually a pretty good section. So here's an inverter, right? So if you recall, this is a PMOS, this is an NMOS. VCC means power supply, this is a ground symbol. That's your quick review, right? PMOS and NMOS devices can be used like switches. And if the input is high, then the NMOS closes, and if the input is low, the PMOS closes, right? And you get that indication from the inverting input into this gate. So another way to kind of think of this circuit is there's two gates, like so, with an output here, and only because of the shared input, only one or the other can be closed, so it's either high or low. Similar to that, it's not ideal, but that's the inverter. This is what we would call a non-abstracted version, or a less abstracted version, compared to drawing it as just an inverter. Because an inverter is this symbol is very abstract. This is less abstract. You can become even less abstract by drawing like the physical representation of it, but that's beyond the scope of this course, so don't worry about that. But we want to start growing more gates, and this can be important to look at and understand how these gates work. And what's going to happen is I'm going to walk you through these. So if A is high, right? And we can draw this in a truth table just to make sure that everything makes sense. So we need to know Y, and we have A and B. So if A is high, this one is going to be open, right? It's off. But this one is going to be on. Now, say B is also high. So I'm starting with 1, 1. Which is a little bit weird, but it's what I did. Okay, so this is, again, off. This is on. B is high, so this is on. And we can follow this trace through, and this is off. So what we have is this nice path to ground, because this is on, so Y sees ground. Okay, so what if we go the other direction? They're both zeros. Well, 0 means this guy is on, right, because it's inverted. This is off, and this is on. So both of these are pulling up to VCC, which is 1. Now, we have two other situations that are slightly more complicated. Okay, so let's follow what happens if only A or B is on. Okay, so if A is on, then when I say on, I mean high. So A turns high, this switch is on, but B is not, so it's closed. So any current trying to flow through here is blocked by either one of these being off. So if A is off or B is off, current cannot flow through here. So what that means is it cannot be 0. Is it 1? Well, if A is 1, this is connected to VC, so it actually doesn't matter what Q3 is doing if Q1 is connected. And similarly, if B is on, rather 0, right? So 0 means this is connected. Then this is pulling to VCC. So as long as either one of them is 0, they're connected to VCC, and they cannot be connected to ground, which means we get 1, 1. So does this mean this is an AND gate? Well, yes, because an AND gate would be 0, 0, 0, 1. This is the opposite of that 1, 1, 1, 0. So you can walk through gates like that and see if it functions like you'd think, and then start imagining ways that you might start making a 3-input NAND gate. I think that's in the homework. It's pretty fun. So here's a NOR gate. It does function like a NOR gate. What does a NOR gate do? Well, an OR gate looks like A, B, and Y. I'm sorry, my B's are looking really bad today. So this is our OR, right? And if we're OR, this is a 1, this is a 1, this is a 1, that's a 0. So what you're looking for is a NOR gate, right? Because that's what it says. And go prove to yourself, pause the video, whatnot, that these switches will behave opposite of an OR gate, because we're looking for NOR. If you need an AND or an OR gate, you build one of these and then just add an inverter. So this is kind of why the NANDs and NORs are universal gates, is because they only take 4 inputs, or 4 transistors to make them, and then to make an AND it takes 6. Okay. This will give you a little bit of a hint when you get to the homework of how you start thinking about these in order to just extend the number of inputs going into them. So instead of having a 2-input NOR gate, you could have a 3-input NOR gate. Yeah, so this is showing the OR gate with this inverter, right? So this is just a NOR, and then there's an inverter here to make it an OR. Okay, so this is another idea that we need to get into once you've understood that's called open drain. So open drain are not used that often, but they will exist. And all that happens is on an open drain, let's only pay attention to this output. So this is an AND gate with an open drain. So what this means is that this node here, you'll notice, never asserts high. There's no way for this node to go high. It can, however, be pulled low, right? Because there's no switch going up. There is a switch going down. So it is 0 or question mark. Now that may not seem very useful at first, but if we flip to the next circuit that is actually useful, you'll see that they add this pull-up resistor. What that pull-up resistor does is if it's 0, it pulls it down to 0 and current flows through. If it's not 0, then this pull-up resistor pulls it up to 1. So this resistor is fairly large in order to limit current. Some of the issue is it's pretty power hungry, and it's not very fast, and resistors are not great for designing in circuits. Couple of minor issues, really. The speed is the biggest issue probably in this. So that's what open drain is used for, is for wire ORing, right? So if I want to output 2 connections, you could have a situation where this is 1 and this is 0, and if you weren't having an open drain, they'd fight, and this one would dump out a ton of current, and this would absorb as much as it could, and you'd potentially fry these devices. That's problematic. Having the open drain means I can do a wire ORing, which is kind of nice, but why not just design an OR gate, right? A more useful concept is tri-state outputs. What tri-state outputs do is they add a third idea where you can have either 1 as an output, 0, or high Z, or high impedance. So Z is kind of the symbol for impedance, and just because impedance is a big word, I guess. And so we say high Z. What that looks like in, say, a buffer is there's a third signal that is enabled, right? So I can turn it on or off. What that means is, let's go look at the circuits, because we understand these circuits now. We understand that they're basically just switches. And this is a nice tri-state buffer, okay? It's going to be inverting because everything is inverting these days when we design in circuits, isn't it? Okay. So if I have an A as our main input, you'll notice that these outside are basically just the inverters. So if A is high, this guy is off, this guy is on, so we get ground. If it's low, this guy is off, this guy is on, so we get high. But the issue is Y can't see that unless enable allows it to. So let's follow enable in. So enable comes in, goes down here, turns this guy on. It's inverted and turns this guy on. So you'll notice that these guys these two, Q3 and Q4, are both either on or off together. If they're off, anything looking into this output just sees a floating wire, right? Because, similar circuit, right? It has two switches with an output, but even though there's something up here and something down here, current has no way of getting to either one of those. So it's just a floating node, so it's basically not there. So tri-state is useful because now you can have a single port that can take turns being an input or an output. Very useful. That's the whole section. If you have questions, feel free to email me. I went through it kind of quick just because I'm cramped for time, and I apologize for that. But I'm more than happy to answer questions via email, Zoom, or office hours. Good luck, guys.